In section 2, we look at the probability that deals with multiple events. In other words, P, the probability of A and B occurring, the multiplication rule, is the probability that event A will occur in the first trial and event B will occur in the second trial. So instead of one simple event, we're looking at two different events. And so what is the probability that both events will happen? And of course, it can be more than just two. There is a key consideration, though. Care must be taken to determine whether or not the events A and B are independent. There is a difference between calculating the probability of randomly selecting a 10 and then randomly selecting an ace from a deck of cards when the 10 was not put back into the deck before selecting the ace. Point of fact, we start out with 52 cards. If I pick the 10, I only have 51 left. So the total number has changed. Therefore, the probability of getting that ace is different than if I had put the 10 back into the deck and I had 52 cards again. So we need to always check, are events A and B independent or dependent? Replacing the 10 in the deck before selecting the ace makes the two events independent. In other words, selecting the ace, the probability of selecting the ace has nothing to do with the fact that I chose the 10 the first time. So, here's an example of randomly selecting two subjects without replacement. This is a polygraph test and the results from that. So we have positive results, so note the word positive in both of these, and it's split into two groups because even though the polygraph test had a positive result, which means the test is saying the subject lied, some of those will be false positives, the subject didn't really lie. In other cases, the polygraph found out the truth. The subject did lie, and the polygraph caught them lying. And then here, negative results, note the two negatives there. This says the polygraph test said the subject did not lie. And again, in some cases, they will match. 32 of our subjects didn't lie, and the polygraph said they didn't lie. Well, there were 9 cases in which the polygraph said they didn't lie, but they actually did. They faked out the polygraph test. And that's why they're called false. So, what is the probability of getting a positive test result first, and then a negative test result second? So, first positive. This is positive, that's positive. Put the two together, that's 57. All 4 boxes is the total number of outcomes. So our first choice was 57 out of 98. Notice in our second choice, we got the 41. The 41 comes from 32 and 9. That was a negative result. So there were 32 and 9. That's 41. But note how the denominator went down by 1. That's because once I made that first choice, since I didn't put it back into the pool to possibly be selected again, I only had 97 choices left as a total possible outcomes for my second choice. Now, here's the multiplication rule. 2 events. Event A, my first choice. Event B, my second choice. Multiply the 2 together, and I get my answer of 0.246. So, as I said, this section is all about multiple events, and we basically multiply our different probabilities. Now, we can also have what's called a conditional probability. A conditional probability is written this way: the probability of B given that A has already occurred. So this would definitely be a dependent case. But really what you're saying is, I know A has happened, so what's the chance of getting B now that A has already occurred? Please note, if you reverse the letters, then it's the event that A occurs given that B has already occurred. And in general, you will not find that reversing them makes these things equal. In other words, PA/B and PB/A are generally not the same thing. Also, if this is true, that PB/A just equals PB, probability that B happened, and that PA/B is just the probability that A happened, then we say A and B are said to be independent because the first part didn't matter. We still got the second part in both cases. Another formula for doing the probability of getting B, given that A has already happened, can be written this way, which is, this is basically the probability of A and B both occurring at the same time divided by the probability of just A happening. And we'll look at an example of that. So let's suppose we wanted to know the probability that it was a positive test result, knowing that the subject actually lied. Well, we know that 51 of the 98 subjects lied for the second part. That would be our PA. We know they lied. Well, if we go did lie, 42 and 9, that's 51. So 51 of the 98 subjects did lie. That's our second part. We know the subject lied. Of those that lied, only 42 had a positive test result. That's right here. Positive stands for positive test result. The polygraph caught them lying. So PB/A equals 42 over 51. However, using this formula here, what about PA and B? In other words, what's the probability of a positive test and they lied? So both of these at the same time. One event, both true at the same time. Well, that's this box right here. A true positive. It was a positive test result and they did lie. That's 42 out of 98. We also know that PA, the probability the subject lied, was 51 out of 98. So 42 out of 98 divided by 51 out of 98 gives us that 42 out of 51. And as I mentioned, generally speaking, this is not going to be true. So all of that, and really in some respects it's a little bit more complicated looking than it really is, but in all of that we get to what's called the formal multiplication rule. In other words, the probability that A and B will both happen. Well, we write this for dependent events, and another way of looking at dependent events is without replacement. In other words, we draw a card but we don't put it back into the deck before the second card. And then it looks like this if the two events are independent, or we are doing with replacement. Okay? So slightly different depending on whether we have dependence in our second choice or not. Now, sometimes, just because things are not significant, we can use what's called the 5% rule, which is even though they are dependent cases, if the sample size is no more than 5%, we can treat the dependent cases, in other words, the without replacement cases, as if they are independent, as if they were actually with replacement, to simplify cumbersome, awkward, tedious calculations. This is because for large numbers, subtracting 1 is not a significant measurement. And we'll look at an example of that shortly, and you can see its use. All right, then we have the probability of at least 1. Okay, so the idea of the probability of at least 1 is the probability that after several trials, there is at least one occurrence of some specified event. Now, please understand, when we say at least 1, that means it could happen once, twice, 3 times, 4 times, however many times we were running into trials. Now, that could be a lot of work, but we can use the complement of at least 1, and the complement of at least 1 is none. In other words, if the answer is none, then there are no at least once because it didn't happen at all. And so I can find the probability of at least 1 to equal 1 minus the probability of none. For example, What is the probability there is at least one girl in a family of 3 children? Now, that would be 1 girl, 2 girls, or 3 girls. A number of different situations. But at least 1 girl is going to be the complement of no girls. So if I go find no girls and subtract it from 1, that will give me the probability of at least 1 girl. No girls, the probability of having no girls is the same as having all boys. And the probability of all boys, since we're assuming it's 50-50, whether you have a boy or a girl, well, that's just 1/2 times 1/2 times 1/2, because all 3 are boys. So the chances of having all 3 boys is just 1 out of 8. Again, assuming that the gender is equally likely. It is often useful to let an event A represent the specified event so that A equals at least 1 girl of the 3 children. Then not A equals no girls. Well, the not A, no girls, was 1 out of 8, all boys. Therefore, the probability of having at least 1 girl, 1 minus 1/8, or 7/8. So it's a little bit easier sometimes to do the none case than it is to work out all the possible combinations of 1 or 2 or 3 and so forth. Here's another example of using the at least one. Suppose the probability that the manufacturer makes defective is 0.0003. Okay, so it's very, very small. We want to know what is the probability that at least 1 tire is defective out of 100 tires ordered. That's the defective rate. Okay, but we want to know if we order 100 tires, what's the chance that at least 1, it could be 1 or 2 or 10, whatever, but we want to know what is the chance that at least 1 out of the 100 tires is defective. Well, if we let the probability of A be at least 1, then not A means no tires are defective. And the probability of not A is 0.9997. That's 1 subtract the 0.0003, 0.9997. Now, we're going to do 100 tires. So it's 0.997 times 997 times 9997 100 times. Or, in exponent form, 0.9997 to the 100th power. Well, that equals 0.9704. So the chances of having no defective tires, I mean, that's not a very big number there. No defective tires is 0.9704. So we subtract from 1. The chances of having at least 1 defective tire is only 0.0296. So just under 3%. So those are the important ideas in section 2. Now let's look at some examples. So, first off, what is the probability of selecting a 10, then selecting an ace with replacement? So that means we pulled a 10 out of the deck of cards, then we put it back into the deck of cards before we picked the ace. That's with replacement. So, because it's independent, we have the whole deck there again. This is simply going to be the probability of selecting a 10 times the probability of selecting an ace. Well, there are 4 10s out of the 52 cards. There are 4 aces out of the 52 cards. So 16 divided by 2704 possible combinations, or 0.00592. On the other hand, what is the probability of selecting a 10, then selecting an ace, but we don't put the 10 back into the deck when we want to select the ace? So here, this is without replacement, and notice the top part's still the same. There's still 4 10s, there's still 4 aces, but where for the first selection we had 52 cards, for the second selection we only have 51 cards, and therefore it had to go down 1 because we didn't put the 10 back in. So now we get a slightly different number, 0.00603. Now you might say, well, you know, what's the importance of doing that? Well, we're only doing 2. We could do this for all 5 cards, and then you keep multiplying, and the denominator would keep going down as a result. So, next example. Assume that birthdays fall with equal frequency on each day of the week. What is the probability that 2 people are born on the same day? Well, the probability of the same day is going to be the first. In other words, the probability of the first person being born on a day, and then the second person being born on the day. Notice the probability for that first person is a 1. If they're born, it's one day of the week. We don't know which day, but it's one of them, so that's 100% accurate. In other words, if they're born, it was on one of the days of the week. On the other hand, the second person, they have to be born on the same day as the first person, and there's only one of those days of the week that's going to work. So 1 times 1/7 gives me 1/7, or 0.143. The second person was independent of the first person, and so that's why it adjusted there. Now, what is the chance that 2 people are both born on Monday? And as you can see, again, first times second, notice that they're both 1/7. Well, for the first person, the chance of being born on Monday, well, there's 1 day out of the 7, so that's 1 out of 7. The second person, the chance for them to be born also on the Monday is 1 out of 7, and so 1 out of 7 times 1 out of 7. The reason I say the second person is dependent is whatever day of the week the first person was born is when the second person has to be born. And so that's why it's 1 out of 7 and 1 out of 49, or 0.0204, just over 2%. All right. Suppose we take 3 of 98 test subjects from the polygraph test. So that is the table that we had on the first page. So this table, there's 98 total. We're going to take 3 of them. They are randomly selected without replacement. So the first question is, what's the probability that all 3 of them had positive results? Okay, actually false positive results. Well, if I look, 15 had false positives. So for my first choice, it's 15 out of the 98. Now, since this is without replacement, once I had that first choice, I now have 1 less false positive to choose, and I have 1 less of the total number of 98 to choose. So note how both of those went down by 1. And now I have 2 people, or 2 selections. And then here, they both go down again, because that third choice, since it's without replacement, these 2 choices are no longer part of the pot to choose from. And so 13 out of 96, or 0.00299. So about 0.3%. Now, what is the probability that all 3 had incorrect test results, either false positives or false negatives? So, for my table, 15 had false positives, another 9 had false negatives, 15 and 9 is 24. So my first choice, 24 out of 98. But since this is without replacement, the second choice is 23 out of 97, because one of those false positives is no longer in the list. And my third choice has 22 out of 96, because now 2 false positives are no longer selectable. So multiply those 3 together. This is why this section is all about multiplication, and we get 0.0133. Now, we're going to look at part B again. What's the probability all 3 had incorrect test results, either false positive or false negative, but this time it's with replacement. Notice the difference between there and here. It's 24 out of 98 all 3 times. Because since I put the selection back into the pot, I still have 24 positive, or false positives or false negatives, I still have 98 total people to select from. Same thing for number 3. I put them back in the pot, so I have equal numbers. And sometimes it's easier to just do this in exponent form, so you would do 24 divided by 98 and then to the third power, and this is 0.0147. So about one, almost half, just a little bit more than the previous case. All right. Only 0.05% of pacemakers are defective. What is the probability that in selecting 20 out of 100,000 without replacement, none of the pacemakers are defective? After all, you don't want to have a bad pacemaker that somebody will die. Now, 0.05% as a decimal is 0.0005. That's the percentage rate. So if I do that times the 100,000, there are, out of that 100,000, there are 50 pacemakers that are defective. But it also means there are 99,950 that are okay. So, since this is without replacement, my first choice to get one that's okay is going to be 99,950 out of the 100,000. Now, since this is without replacement, notice how this went down. 99,949 divided by 99,999. And then 99,948 divided by 99,998. And then the little dot here is because I got to do 20 of these going down each one. However, 0.005 and the 20 out of 100,000, all of that is way less than the 5% rule. So instead of doing this, I'm going to treat it as if it was an independent case. So just the first one raised to the 20th power, I get 0.99. So what is the probability that in selecting 20 out of 100,000 are going to be fine? 99%. All right, so number 5 here, give a written description of the complement of the given events. So here was the given event. When Jose asks 5 different women for a date, at least one of them accepts. We want the complement to this statement. So when Jose asks 5 women for a date, none of them accepts a date. So notice how similar the two are. At least one, the complement is none. Most of the other words in the two sentences are exactly the same. What changed is this was at least one, its complement was none. Okay, a second example. When 6 defibrillators are purchased, all 6 of them are free of defects. Okay? Now, its complement. When 6 defibrillators are purchased, at least one of them has a defect. If not all 6 are bad, one of them at least has to be bad. Now, some people get confused because here, at least one was the complement of none, and here, at least one was the complement of all. It just depends on how your statement is worded. For instance, instead of saying all 6 of them are free of defects, I could have said none of them are defective. If all are free of defects, then none of them are defective. In either case, the at least one has to be the complement. All right. The credit rating FICO, which stands for Fair Isaac and Company, has a 1% delinquency rate for consumers with a credit above 800. If 4 customers are randomly selected, find the probability at least one is delinquent. So we're going to look at that none case again. If we say that the probability of A is the probability of at least one, then the probability of not A is the probability of none. Now, If 1% are delinquent, that means 99% are on time. So the not A case would be the 0.99 to the fourth power. Or the probability that none of them will be delinquent is 0.9606. Well, since the probability of at least one has to be 1 minus the probability of none, 1 minus 0.9606 is 0.0394, or just under 4% have a chance of being delinquent if they select 4 customers. All right, we're back to our polygraph test results. Find the probability that a subject lied given a positive test result from the polygraph test. So here's our polygraph test for a minute. We want the probability that the subject lied given a positive test result. So these are all the positives, and we want to know the probability that of all those positives, we got they actually did lie, that the polygraph was correct. So both A and B, positive and lied. That's the 42, 98 for all 4 boxes. So 42 over 98. PA is for positive test result. 42 were positive, another 15 were positive, so between the two of them, there are 57 out of the 98. So finding PB/A, the probability that the subject lied given a positive test result, 42 out of 98 over 57 out of 98 gives me 42 out of 57, which is 0.737. So there is almost a 74% chance that the subject did lie knowing that you had a polygraph test result. Now, I point this out because this is not the same answer in my example on the first page. This was, what is the probability of a positive test result given that the subject lied? So we're doing the opposite. Notice that it is not simply flipping things around. This had an answer of 42 out of 51. This one had 42 out of 57. So they had the same numerator, the A and B case, but the denominator was now different. So switching A and B does not give you a reciprocal or something like that. It's a totally different probability. And then our last example, an entire batch of aircraft altimeters will be rejected if there is at least one defect. If the defective rate is 3%, what is the probability the batch will be rejected if the batch contains 4,000 altimeters and 100 of them are selected without replacement and tested? So first off, altimeters are what a plane uses to tell how high it is off the ground. And again, we got 4,000 to choose from. We're going to pick 100 of them without replacement and test them. The defective rate is 3%. If even one of the 100 is bad, we reject the entire batch of 4,000. So, first off, 3% is less than 5%, so we're going to use the 5% rule. We're picking 100 out of 4,000, so it's definitely less than 5%. Now, if 3% are defective, then 97% are okay. So the none case, in other words, all of them are okay, would be 0.97 to the 100th power. We're selecting 100 of them. And that comes out 0.04755. The at least one case will be 1 minus the none case. So 1 minus the 0.04755. The probability at least one of them will be bad, 95%, 0.952. So there is a high probability that at least one of them will be bad. And that wraps up Section 3-2.